Welcome to The Explainer. Today, we're unpacking something truly groundbreaking. We're looking at Michael Gutman and Aapo Hyvärinen's 2010 paper on unnormalized statistical models. You know, if you've ever found yourself wondering how modern AI processes just massive mountains of complex data without bringing your computer to an absolute grinding halt, well, the math we're diving into today is a huge part of that answer. It introduced noise contrastive estimation, or NCE for short, which was literally a game changer for a problem that had stumped researchers for years. So here's our roadmap for today. We'll start with the normalization problem, then jump into the NCE solution, explore learning by comparison, see what happens when putting it to the test, and finally look at modeling natural images. Section 1. The normalization problem. Let's set the stage by looking at the absolute computational nightmare data scientists were dealing with before this solution came along. Back then, when researchers were building statistical models, they essentially had to pick their poison. On one hand, you could play it safe with constrained, normalized models, much easier on the computer, but pretty limited in what they could actually do. On the other hand, you could choose unnormalized models, like Markov random fields or multi-layer networks. Now, these are incredibly powerful and expressive, but they come with a brutal mathematical penalty. They are ridiculously difficult to process.
And that penalty boils down to one massive bottleneck, the normalization constant, sometimes called the partition function. See, in probability, all possible outcomes have to add up to exactly 1, or 100%. Simple enough, right? But to force an unnormalized model to obey this rule, you have to calculate an integral over every single possible state of your data. If you're working with high-dimensional data, like, say, high-resolution images, that calculation is rarely analytically tractable. Honestly, it's a computational nightmare. It takes way too much computing power.
Which brings us to Section 2, the NCE solution. Let's look at the incredibly elegant aha moment the researchers had.
They realized that they didn't have to play by the traditional rules. Instead of treating that normalization constant as this massive, impossible calculation that absolutely has to be solved up front, they just bypassed the roadblock entirely. They simply labeled it C, tossed it into the model as an unknown variable, and let the model figure it out during training, alongside everything else. I mean, it sounds almost too simple, right? But traditional maximum likelihood estimation couldn't do this. It would just push the constant to 0 to artificially inflate the likelihood. So the researchers needed a totally new way to train the model to find all the correct parameters, including C.
That leads us perfectly into Section 3, learning by comparison. How do we actually train this thing in practice?
Well, the entire philosophy of the paper can really be boiled down to this one brilliant, highly digestible thought. The idea behind noise contrastive estimation is learning by comparison. They essentially mapped a really difficult unsupervised learning problem directly into a straightforward supervised classification problem. Okay, let's break down exactly how they achieve this with a simple three-step recipe. Step 1, you take your actual observed data. Step 2, you artificially generate a bunch of contrastive noise, maybe using a basic Gaussian distribution. And step 3, you train a nonlinear logistic regression classifier to just spot the difference between the two. That's it. By forcing the model to constantly compare real data against fake noise, it inherently learns the true underlying structure of the real data. And because it's only doing binary classification, just asking, is this real or fake, it completely avoids having to calculate that impossible normalization integral.
Now you might be thinking, is this just a clever hack? Absolutely not. The authors backed this up with rock-solid mathematical proofs. They proved non-parametric estimation, meaning with enough data, the classifier perfectly finds the true data distribution without any normalization constraints at all. They proved consistency, so as you feed the model more samples, its estimates reliably hone in on the true parameters, including our sneaky little variable C. And they proved asymptotic normality, which is just a mathematically rigorous way of saying the estimation error shrinks predictably as your dataset grows.
Let's move on to Section 4, putting it to the test. Theory is great, but we need to see how it actually performs in the wild.
To test their claims, they set up an independent component analysis simulation, and the results for mean squared error were exactly what you'd hope for. As the sample size scaled up, the error for the noise contrastive estimation method steadily and smoothly dropped right down. It zeroes in perfectly on the true parameters. This is that consistency proof we just talked about happening right before our eyes.
But the ultimate payoff here is the sheer efficiency. When you evaluate estimation accuracy versus computational time, NCE achieves top-tier precision in a mere fraction of the time compared to its rivals.
It gets highly accurate results so much faster than older methods like contrastive divergence or score matching. It's just wildly efficient.
So the crucial takeaway here is that NCE empirically offers the absolute best trade-off between statistical accuracy and computational efficiency. It drastically outpaces maximum likelihood with importance sampling. It gives you way more stable, lower variance results than contrastive divergence, which, by the way, was hugely popular at the time. And unlike score matching, NCE doesn't force you to make weird, smooth approximations of your data just to get the math to work. It handles the raw reality of the model gracefully.
All right, Section 5, Modeling Natural Images. Let's bridge the gap between abstract theory and actual, tangible applications. The researchers decided to unleash their method on raw, whitened natural image patches to see if NCE could independently map out true visual reality. They took 30 by 30 pixel crops of wildlife scenes from the Van Hateren database, stripped out the basic redundancies, and basically just asked the model to figure out the complex visual structures purely by contrasting those real images against uniform noise.
And the visual proof of success is just striking. When using a two-layer patch model, NCE naturally learned to pull together features of similar orientation, essentially mimicking the complex cells we actually have in our biological vision systems. And when using a Markov random field model, it learned these highly structured, high-frequency Gabor-like filters. Think about that for a second. The model figured out the fundamental building blocks of natural images entirely on its own, incredibly fast, without ever having to compute that impossible normalization constant.
We'll wrap up this explainer by leaving you with a bit of a provocative thought. How does this foundational principle from 2010, contrasting signal against noise, govern the massive deep learning architectures we rely on today? Gutman and Hyveren's realization that we can bypass impossible math just by teaching a model to discriminate between real data and fake noise, it didn't just solve a niche statistics problem. It laid the crucial groundwork for modern representation learning. When you look at today's massive large language models and advanced image generators, ask yourself, how much of their incredible speed traces right back to this elegant, simple idea of learning by comparison? Thanks for joining me for this explainer, and keep questioning the math behind the magic.